Okay, so we're going to start. It's going to be broken up by the test on Thursday, but we're going to start discussing a topic called Markov chains. I always enjoy this topic because it gives very concrete applications of linear algebra to a variety of subjects. I think that's something that this class can sometimes lack. So a Markov chain or a Markov process occurs in the following situation. You are looking at some kind of system, and this system takes on states. So for one example that we'll look at later today, maybe you're looking at an epidemic or the spread of a disease, and the system is a human being, and the state is that that person is sick or that person is healthy. You know, something like that. And periodically, state changes can occur. So a sick person can get well, a healthy person can become sick. And the last condition, what makes a process a Markov process, is given any two states, the probability of transitioning from one to another is fixed. And that is a very important condition that prevents a lot of processes that look like they might be Markov from actually being Markov. Let's try to illustrate this by looking at two examples involving disease. So examples that sort of on the top of it might look similar. We are going to look at, let me find my notes. Tuberculosis in Ghana. First of all, as an example of a very concrete, very real-world situation that was productively studied using Markov processes. And in particular, this was studied using the famous SIR model, where people can be susceptible to the disease, or they can be infective or infected. You sometimes see both. Or they can be recovered. You also see R used for removed sometimes. People who are, for whatever reason, removed from the situation. Maybe they have recovered and the disease granted them immunity from further infection. Maybe it's a fatal disease and they have been removed by death. But they are removed from the model in some way. So the classic SIR model says that people transition like this. They go from susceptible to being infected to being removed. And there are a bunch of things you could do to this model that to modify it to fit the parameters of a particular disease. So perhaps you have a disease that is sometimes fatal and does not provide immunity upon recovery. Then from infected, you could either be removed or you could go back to being susceptible. And there are, again, I mean, this is not an exaggeration, probably literally thousands of little variations of this model that have been published at some point or another. It's extremely, extremely famous. Maybe you want to include a vaccinated category, and then maybe you want to include the possibility that even though you're vaccinated, a breakthrough infection occurs. But let's just look at this. So, first, particularly looking at this in the context of that last condition, that given any two states, the probability of transitioning from one to another is fixed. That we have finitely many states, that's clear. We've got an S state, an I state, an R state. That periodically state changes occur. I mean, I wouldn't necessarily use the word periodically, but you could check somebody's health every day at midnight. And every day at midnight, they're in whatever category they're in. So you can think of this as occurring periodically. Are the transition probabilities fixed? I mean, presumably, absent any kind of medical care, the probability from going from I to R is fixed. I believe that tuberculosis is fatal, so a person will have it for however many years until they pass away and are removed to R. So we can perhaps think of this transition probability as being fixed, where certainly waving some details under the rug, or that's a mixed metaphor, or certainly sweeping some details under the rug. But all mathematical models are going to be models. They're approximations of the real world. So we probably can treat this as being fixed and not cause any trouble. What about this probability? What about the probability of moving from S to I? The probability of getting tuberculosis? Well, in this particular context, that probability can probably be treated as fixed as well. And that's because in this particular context, tuberculosis was being caused by improperly sterilized barbering equipment. So you shave every day, there's a 0.5% chance that you nick yourself. There's a 0.1% chance that if you nick yourself, you get yourself tuberculosis. I mean, you can think those probabilities are just made up. They're not reflecting the actual situation in Ghana. But you can see that there's no real reason that this transition probability should be changing over time. So it does make sense to think of these transition probabilities as being fixed. And as I say, this is not some, theoretical thing I made up before class. This is based on a real paper that I did read during my dissertation research. So this model has factually been used to study tuberculosis, and in particular, this model has been used to study tuberculosis using the tools of Markov chains. If we now want to look at an example where a Markov chain is completely inappropriate, in spite of looking similar, we could look at COVID in Nebraska. And we can keep SIR R is now going to stand for resistant. Somebody who has had COVID gains resistance to being reinfected, but they can get COVID a second time. We can go from susceptible to being infective to being resistant. COVID, I mean, it would be, even though it's a little morbid, it would seem disingenuous to deny that COVID resulted in a lot of deaths. Let's have that as its own category. Resistance is temporary. Eventually, a resistant person will go back to being susceptible. And we're talking about COVID in Nebraska pre-vaccine, so there's no vaccinated category or anything of that nature. Well, this seems very similar to this, and it certainly satisfies two of these conditions that I have on the whiteboard. There are finitely many states. Again, the periodically is a little artificial, but you look at somebody's health at the end of every day. You don't worry about, well, did he get COVID at 1:15 or at 3:20? Just at the end of the day, he might be sick or he might not be. But this is not a Markov chain. The Markov chain would be a completely inappropriate tool to use here. And that's because over the course of the COVID epidemic, the probability of going from susceptible to infective has been in no way constant. I mean, think of our experiences here in Chadron. At the start of the epidemic, there was nobody in all of Nebraska who was sick. People were sick in New York, but they were not sick here. So with nobody sick in Nebraska, the probability of getting COVID in Chadron was functionally zero. I mean, as long as you weren't traveling a lot. Then the epidemic really began in earnest. People started getting sick in Nebraska, but still there weren't any cases in Chadron because Chadron is so isolated. The cases were all in larger cities. So again, for us in Chadron, there was still an extremely small probability of going from S to I. But not a zero probability, and eventually a few people in Chadron did get sick, and then more people got sick, and then college students converged to Chadron from, Thanksgiving break and stuff. And the probability of going from S to I, that is, the probability of getting COVID, was increasing very quickly. Then vaccinations happened. We had a maybe slightly abortive, but I would say successful, social distancing, mask mandates, etc. And the infection rates began to drop. So the probability of going from S to I has changed radically over the course of the outbreak. It is very much not something that you can treat as being constant. So even though these things look similar, one of them can be studied using Markov chains, whereas the other cannot. So Markov chains are a very powerful tool, but they do have their limits. As an example of something that you might think of as a Markov chain, as a simpler example, you might think of signal transition. And for simplicity, let's just look at an individual bit of data. I mean, an actual signal would contain significantly more than the one bit, but you are transmitting bits of data, so you're transmitting ones and you're transmitting zeros. And what, of course, you would like to happen, ideally, is that if you transmit the 1, the receiver receives a 1. And if you transmit a 0, the receiver receives a 0. But transmission errors do occur. It does happen that sometimes you submit a 0 and your receiver gets a 1, or you transmit a 1 and your receiver gets a 0. So we have these two states. Our states are 1 and 0. We have the transmission. Ideally, transmission will send these states back to themselves. But it can also cause a state change. And unless you're doing something special to change the probabilities that your transitions occur effectively, these transition probabilities are presumably pretty much fixed. Like if from one day to the next you're using the same transmission equipment and the same receiving equipment, there aren't any like wild weather patterns that are messing with your electronics. This is presumably a Markov chain. You have finitely many states. You have 2, 1 and 0. You have periodic transition between the states. Notice that a transition between the states can result in the state being the same, though. So if we transmit and our 1 stays a 1, we can still think of that as a state change. It's just changing to itself. The transition probabilities are presumably fixed. So this is a Markov chain. So Gambler's Ruin, and you can tell an example is famous if it has its own name. But Gambler's Ruin looks like this. You have some finite you go into a casino with some amount of money, say $10, and you bet some fixed amount of money, say $1. So you could lose, in which case you go from 10 to 9, or you could win. Let's just, for simplicity, say that a win on $1 bet will result in a $2 gain. Obviously, real casinos are more complicated than this, but now you keep betting. From 12, you could go to 11, or you could go to 14. From 11, you could go to 10, or you could go to 13. From 13, you could go to 12, or you could go to 15, and so on. From 11, you could go to 10, and you are going to keep doing this until one of two things happens. One, you win some fixed amount of money. You go in there with $10 and you say, I'm not walking out until I have $100. Or you could go bankrupt, in which case you cannot, of course, gamble anymore. So this is an example of a Markov chain. There are finitely many states. If you're gambling until 100, the last state is actually 101, because you could have $99, win $2, that will bring you to 101 rather than to 100. But you have finitely many states. The probabilities of transitioning between these states are perfectly fixed. You have the same win probability or the same lose probability every time, as long as you are playing a game of pure luck, like slots or something, and as long as you're not changing the game you're playing. So here's a pretty classic example of gambler's ruin. In fact, probability as a field it was developed by gamblers. I mean, it's not a very prestigious beginning, maybe, but people wanted to bet, and they wanted to know how likely they were to make money on a bet, and that's how the field of probability came into existence. So, not real surprising to see it represented here. So, these are just a few examples of Markov chains. And we want to use Markov chains to answer questions. I mean, take this gambler. If the probability of winning $2, if the probability of winning $2 is always 0.45, and the probability of losing your dollar is always 0.55, And this guy comes into the casino with $10 or $20 or however many dollars. What's the probability that he just loses his money versus the probability that he walks out of the casino with $100? I mean, very concrete, very natural questions like this that we want to answer. Any question about sort of what a Markov chain is, what we're trying to do with it? So another example of a Markov chain that you know is important because it has its own name is a random walk. Let's give a random walk example, and then let's use this as our gateway into actually doing some linear algebra. A random walk occurs. I mean, in one sense, all Markov chains are basically random walks. It's just that a random walk is a very literal way of thinking about it. We have some states. State 1, state 2, state 3, and state 4. And these states, we can think of them as physical locations, like buildings on a block, and somebody is physically then walking up and down the street. So from state 2, we can go to state 3 or state 1. From state 3, we can go from state 2 to state 4. From state 3, we can go to state 2 or state 4. Traditionally, in a random walk, well, it depends heavily on the situation, but often in random walks, these end states only go to themselves. So we have these two states, and once you're in one of those states, you just stay there forever. So let's say that all movement occurs with equal probability. That is to say, here are our transition probabilities. If we're in state 1, we go to state 1 with a probability of 1. If we're in state 2, we go to state 1 with a probability of 1/2. We go to state 3 with a probability of 1/2. If we're in state 3, we go to state 2 with a probability of 1/2. We go to state 4 with a probability of 1/2. And if we're in state 4, we remain in state 4 with a probability of 1. Note, by the way, there are a bunch of transition probabilities that I'm not bothering to write down because they're all 0. Like the probability of going from state 1 to state 2 is 0. So I'm not bothering to write that probability down. Let's ask the question. Suppose that initially you are in some randomly selected state. So maybe you're in state 1 with my notation here is going to be ugly. Okay. Well, I'll live with that. You're in state 1 with initial probability 1 sub 0. And you're in state 2 with initial probability 2 sub 0. State 3 with initial probability 3 sub 0. And state 4 with initial probability 4 sub 0. And now you ask, after one transition, what is the probability of being in each state? Let's try, have all of you taken some kind of elementary probability with Detson or in high school or... Okay, so let's call 1 sub 1 the probability of being in state 1 after one transition. Well, there are two ways that this could happen. We could be in state 1, and then we could stay in state 1. The probability that we are starting in state 1 is 1 sub 0. The probability that we stay in state 1 is 1. How else could we get into state 1 after one transition?
After 2.
Yes, we could start in state 2 and transition into state 1. The probability that we start in state 2 is 2 sub 0. The probability that we transition to state 1 instead of state 3 is 1/2. And then, just for clarity, if we start in state 3, there is a 0 chance that we go into state 1. And if we start in state 4, there is a 0 chance that we get into state 1. What's the probability that we end up? Let's keep these rows distinct. What is the probability that we end up in state 2 after one transition? Well, we could, it's really only one way to get into state 2. I, for some reason, wrote the one arrow twice, but the only way to get into state 2 is to start in state 3 and transition into state 2. So we start in state 3 with a probability 3 sub 0. We transitioned into state 2 as opposed to state 4 with a probability of 1/2. And then quickly scrolling in, we start in state 1 with a probability of 1 sub 0, but go to state 2 with a probability of 0. Likewise, there's a chance we start in state 2, but if we start in state 2, we're not transitioning to state 2. And there's a chance we start in state 4, but if we start in state 4, we're not transitioning to state 4. We're not transitioning to state 2. And the probability we wind up in state 3, well, there's once again only one way to do that. To start in state 3, and I kept writing those extra arrows in, but to be in state 3, we need to start in state 2 and go right. That's the only way we'll wind up there. So we have to start in state 2, and we have to go right. Then all of the other probabilities are 0. Can't go from state 3 to state 3. Can't go to state 3 from state 4. There are 2 ways to wind up in state 4 after one transition. We could start in state 4, and then we remain with probability 1. Or we could start in state 3 and move right with a probability of 1/2. We start in state 1, we don't go to 4. If we start in state 2, we don't go to 4. And what we have here then is a system of linear equations, or more or less a system of linear equations. The vector 1, 1, 2, 1, 3, 1, 4, 1 equals a matrix times the vector 1, 0, 2, 0, 3, 0, 4, 0. In particular, the matrix of coefficients. So 1, 0, 0, 0, 1 half, 0, 1 half, 0, 0, 1 half, 0, 1 half, 0, 0, 0, 1. So to answer this question, if we have some initial probability distribution, what's our probability distribution after a single movement? Well, here we are. We take the initial probability distribution and we multiply it by a matrix and we get a new probability distribution. And this matrix gets a name. It's called the transition matrix. And of course, there's nothing magical about this random walk that let me create a transition matrix for it and only it. I could very easily, or in one sense very easily, create a transition matrix for this Markov chain as well. It would be a significantly bigger transition matrix because there are 102 states. So it would have 102 rows and 102 columns. But there's nothing theoretically difficult about writing it down. And furthermore, the transition matrix would almost all be zeros. So it would be not fun to do by hand, but if you were working on a computer, it would be much quicker. You'd start with a matrix of all zeros, and then tell the computer where the non-zero entries need to go. This is another example, by the way. I only mentioned this in passing, but I said that a lot of really important matrices are sparse, by which I mean they have almost all zeros as their entries. This is another example of that. It would be an extremely sparse matrix, because almost all of the transition probabilities are 0. Okay, presuming that we don't want to go through the trouble of doing that every time we want a transition matrix, we should probably figure out how these transition matrices work. And a transition matrix works as follows. The columns represent the from state. The rows represent the to state. So going back here, the rows represent states. The columns represent states. This 1/2 that we have in the third column, fourth row, says that the probability of going from state 3 to state 4 is 1/2. This 0 in the state 2 column, state 4 row, is the probability of going from state 2 to state 4. It's a 0 probability. So let's do an example of this where we have fewer rows and columns. Let's do the signal transition probability. Let's say that the probability of a successful transmission is 0. Need to leave myself a little more space. Let's say that the probability of a successful transmission is 0.999. So the probability of an error must be 0.001. So even in cases where the states do not, have names, and maybe the states don't have any kind of natural ordering to them, even in cases like that, you're going to have to decide what states each row and each column represents. So I'll let the first row represent state 0, the second row represents state 1. And once I've made that determination with the rows, it's the same for the columns. You're not allowed to let you're so not allowed to do it that even when I intentionally tried to make that error, I instinctively didn't. You're not allowed to have your rows and columns be in different orders. It has to be the same order. And then we can go down. The probability of going from 0 to 0 is 0.999. The probability of going from 0 to 1 is 0.001. the probability of going from 1 to 0 is 0.001. And the probability of going from 1 to 1 is 0.999. And there's our transition matrix. So students sometimes struggle with the following because it doesn't use the word transition, but I mean it doesn't state the initial probability distribution as a probability distribution, but something like this. If you transmit a 0, what is the probability of receiving a 0? And this is simple enough that you don't really need the matrix to do it, but let's approach it using these techniques. The part of this problem students seem to struggle with is the idea that you have an initial probability distribution. It's just that you have 100% probability that you're transmitting a 0, 0% probability that you're transmitting a 1, because the problem is explicitly telling you that you are transmitting a 0. So you take that, your initial probability distribution, you multiply by this matrix, and you get 0.999, 0.001. So this is the probability of receiving a 0. It's 0.999. Well, as I say, if you just wanted to do that, it would hardly be necessary to mess around with these Markov chains. Let's ask a more interesting question, or at least a more difficult one. You transmit a 0, but you're transmitting from a remote location, so it has to go through relays. As a result of which, by the time the person you're trying to contact receives your transmission. It's been transmitted several times. So maybe you want to know, after 5 transitions, what is the probability that a 0 will be received? This is where Markov chains really become useful and become, I would say, a necessary tool. Because I mean, in probability classes, you learn in theory how to answer that. Just find all of the ways that a 0 could be received and find those probabilities and add them all together. But there are so many different ways that a 0 could be received. I mean, you transmit first transmission stays 0. Second transmission stays 0. Third transmission stays 0. Fourth transition, error turns it to 1. But fifth transition, another error turns it back to 0. I mean, trying to count up all of those ways and find all of the probabilities and then add them all up would be pretty overwhelming. Using the Markov chains, it's extremely simple. If you have some initial probability distribution, and you have your transition matrix A, then the probability distribution after K transitions is, instead of just multiplying A by this initial probability distribution, it's A to the power of K times the probability distribution. So this problem, which would be extremely messy to attempt by hand, is actually extremely straightforward. Because we're interested in what happens after 5 transitions, that matrix gets raised to a 5th power. And now, of course, there's absolutely no chance of us doing this by hand. So let's go to our trusty calculator. We now have a 2x2 matrix, 0.999, 0.001, 0.001, 0.999. So there's our matrix A. We have this initial probability distribution, 1, 0. So we'll take this matrix A. There's no special button for a matrix power. We raise it to the 5th like it was a number. We multiply it by the initial probability distribution. And we get that. Up to 3 decimal places, 0.995. Let's end with a quick definition. And a warning. The definition will be that a stochastic matrix has all of its entries stuck between 0 and 1, and has columns that all add up to 1. And as one might expect, since I'm stating this definition immediately after I talked about these transition matrices, all transition matrices are stochastic. And actually, vice versa. Any stochastic matrix is the transition matrix of some Markov chain. As far as that statement goes, statement 1 should be obvious if we think about it a little. The entries of a transition matrix are all probabilities. Probabilities are positive numbers between 0 and 1. What about the restriction that the columns all add up to 1? I mean, if you look at the transition matrices we've written down, it's certainly true that they've all had this condition. And to see where that comes from, remember what the columns of this matrix represent. The columns represent the probability that we start at 2, that if we are at 2, we transition somewhere. The probability that we transition to 1, to 2, to 3, or to 4. Well, It's just how Markov chains work, that if we start at 2 and a transition occurs, we have to wind up somewhere. We have to wind up either at 1, 2, 3, or 4. So the probability that we wind up at 1 plus the probability that we wind up at 2 plus the probability that we wind up at 3 plus the probability that we wind up at 4 has to equal 1. And that's just a statement that that second column sums up to 1. Finally, a dire warning, or not really dire exactly, but I mean, usually if you're like confused by something and you look at the internet, or you look at another textbook or something, that's fine, not going to be an issue. But some, I would even go so far as to say a lot of resources define these things a little differently. And that's because probability is one of the very few disciplines I'm aware of. Sorry, a trainee does not seem to, or mentee does not seem to realize I am in class. Probability is one of the relatively few disciplines where you see a lot of people wanting to use row matrices instead of column matrices. And the reason that's significant is that if you're using row matrices, then for the matrix vector multiplication to be defined, that row matrix has to go in front of the transition matrix. And the result of that ends up being that these sources will define their transition matrices to be the transposes of our transition matrices. So, like the probability of going from state 3 to state 4. I mean, this probability here will be the probability of going from this state to this state, instead of what we've said, which is that it's the probability of going from this state 4 to this state 3. When they define stochastic matrices, it's the rows that have to add up to 1 instead of the columns. So if you are looking for help from outside resources, make sure that you read how this outside resource is defining its things, because it might be defining stuff a little differently than we do. And with that, class is at an end.